question A, we have the function of x is just x. Okay, so firstly, let's just think about it, and then we'll talk about how we can use the first principles formula. This is the equation of a line. Okay, remember, y equals mx plus c is the equation of a line. Here, the value of m is 1, and the value of c is 0. So this is the equation of a line that has a slope of 1 and a y-intercept of 0. So we could even sketch it, right? This is what it looks like, okay? It goes through the point 0, 0, that's its y-intercept, and as x goes across 1, y goes up 1. Now what we have when we have the equation of a line is the slope is the same the whole way along that line. In fact, we know here's the slope, right? Y equals mx plus c. The slope is 1. So if we're going to find the slope function, well, it's going to evaluate to 1. It has to be, because the equation of a line has a slope of m, a value of m here is 1. If we use the first principles formula, okay, so if this is f of x, then f of x plus h means you put x plus h everywhere there's an x, okay? So f of x plus h becomes this. If we put it in the first principles formula, we have f of x plus h, take f of x on top of h. So I'm just going to do it quickly. Thank you. X cancels, so we have h divided by h. H divided by h is 1. And then you would apply the limit. There's nowhere to substitute. H approaches 0, so our value is 1. That's what we expect. Okay, how about this one? If we have f of x equals 1, remember f of x is the y value. So if we have f of x is 1, this is a horizontal line of y equals 1. What's the slope of this horizontal line? 0. It's not increasing, it's not decreasing. Now, if we're going to find f of x plus h, that means we put x plus h everywhere there's an x. There's no x. There's nowhere to put it. So that means f of x plus h is just 1. Now when you put it into the formula, you have 1 take 1 divided by h. We get 0 at the top, 0 divided by h is 0. So that's how A and B work out. All right, but I think the best way to think about them is intuitively. You'll never get asked anything like that. Let's move on to these square root ones then. So this is question 2b in your notes book. And we're going to do question 2b and c together, and then we'll leave those principles for you guys to carry on with. So this is going to be new for us. You haven't done these in year 11. So I'm going to leap straight into the formula. I'm not even going to write the formula this time. I'm just going to substitute everything in and we'll get started. So step 1, put the things into the formula. We have the limit as h approaches 0 of 1 on h, and then in brackets, this f of x plus h, take f of x. Okay, so that's step 1. We've substituted it into the formula. Now, every time we have a radical function, that's a function with a square root or a cubed root or anything like that, we always have to do this one step where we multiply by the conjugate. We can't process this any further. So we always have to do this. And I'm going to explain to you why. We're always going to multiply it by that, except we make it positive. And then divide it by itself as well. And I'm going to explain why this is a legitimate operation. Okay, so that's always going to be one of the steps we have to do whenever we have a radical that we're performing first principles for. All right, so firstly, can anyone tell me what is the square root of x plus h plus root x divided by the square root of x plus h plus root x? 1. It is 1. And that's why this is a legitimate operation, because we're not changing the value of this, we're just multiplying it by 1. We've still got one lot of it. Perfectly acceptable thing for us to do. Now the reason we are doing this, okay, is because we have these square roots here and we want to get rid of them because we can't manipulate it when it's got a square root around it. And if you look, we have the square root, take the square root, and then we have the square root plus the square root. So it's like this. We have a take b multiplied by a plus b. This is the difference of two squares expansion. All right, if you FOIL it or if you expand it, it comes out to a squared take b squared. So it gets rid of the middle term and it gets rid of the square root. So that's why we multiply by the conjugate. Now the conjugate just means you take what's there and you change the symbol. Okay? So if that's, yeah, it's always going to be a negative for first principles anyway. All right, so let's write out what we would have then. And this one I'm going to do slowly and over a number of steps, but this is something that you can sort of skip ahead a bit if you're doing it normally. It's just because I'm trying to draw out exactly what's going on here. So I'm going to write what we've got at the top. And then what we've got at the bottom. Now, so what we've done so far is we've subbed it into first principles and now we're multiplying by the conjugate. Okay, now the process is the same. We've got to expand and collect like terms. And remember, expand the numerator, leave the denominator. Don't touch it. The denominators get incredibly messy. Just leave them and it'll all work out in the wash in the end. So what's going on at the top here then is we have A take B multiplied by A plus B. So we're going to use the difference of two squares rule. What's going to happen next?
Square roots cancel.
That's right. It becomes A squared take B squared. All right. I'll just see if I can use some different colours. So this whole thing is that's broken. This whole thing is A. We have A take away B. We have A plus B. So A squared take B squared. All right, difference of two squares. Okay, so now whenever we have a square root squared, the square root cancels. All right, so let's write what we've got. Now, I'll extend these brackets because they're going over the denominator there. Okay, so we've gotten rid of the square root with the squared. Now we can collect like terms at the top. And remember, leave the denominator. So at the top we have x and x will cancel. So we will have the limit as h approaches 0 of 1 on h multiplied by h on top of okay, so let's take it back. We've multiplied by the conjugate, we've expanded it, we've collected our like terms. Now we're going to factorize and cancel the h. So if I pull the h out the front, can anyone tell me what do I have left at the top of the fraction here? If I pull 1, very good. So we've got h on h here, we have 1 here, because if we distribute it, h times 1 gives us h. Okay, so that'll cancel. Now we're ready to apply our limit.
Do you not take them out of the denominator as well?
No, we only factorise from the numerator. Yep. So that's the h out the front of the denominator. We just keep that out the front for the whole time. H is cancelled. Now let's apply the limit. So we're putting 0 where the h is. What we're going to have is we're going to have 1 on top of root x plus root x. Yeah, because I'm putting 0 there. So that becomes root x, and then I have plus root x. Now, if I have one lot of root x plus another lot of root x, how many lots of root x do we have?
2.
1 on 2 lots of root x. Okay, so that's our f dash of x function. All right, so make sure we're writing the limit all the way through until we get to here. Now, really the only trick here is use the conjugate and difference of two squares. The rest is the exact same. Okay, let's have a look at C. Any questions? All right, this is a nice long one as well. And this is different. It doesn't have a square root in it, but it does have the function is in the denominator, isn't it? We have 3 on top of x squared. All right, so let's go straight to the formula. F dash of x is the limit as h approaches 0 of 1 on h multiplied by sorry, I was totally stuffed that. F of x plus h. There we go. No, this is right. F of x plus h squared, take f of x.
Mr. Rose. One question.
Yep.
Would it be easier to complete it by rearranging the 3 on x squared to 3x to the negative 2?
No.
No?
Nah, yep. So if we don't use negative indices. So
Okay.
that's the thing. We never use radicals and we never use negative indices. Good question though, because like when you first encounter this, that would probably be your temptation
Yeah.
to go down that route. But with first principles, we want things expressed as fractions and we want to get rid of roots.
Yeah.
So at the moment, we've got it expressed as a fraction and we want to perform this operation, right? We're trying to carry out first principles. So I need to do this term, take away this term, but there's one error. They don't have the same denominator, okay? So in order for us to carry out this subtraction, we need to make them have the same denominator. All right, so just as an example, if I have 3/4 take away a half, the only way I can perform this is if I make this have the same denominator. So what we're going to do is cross multiply the denominators. I'll show you here with numbers and then we're going to repeat it up here with the algebra. If we cross multiply, what we're going to do is we're going to multiply this term by 2 on top of 2. We're multiplying it by 1. We're not changing its value. All right, so that's a legitimate operation. Thank you. All right, so we're not changing its value. Here, we're going to multiply it by 4 on top of 4. Again, we're multiplying it by 1. We're not changing its value. So on the left-hand side, we'll have 6 on 8. On the right-hand side, we're going to have 4 on 8. They now have the same denominator. That's something you can perform. You can even express it as 6 take away 4 on top of 8. You can bring it over the same denominator. Okay? So that's what we're going to do here, is we are going to cross multiply the denominators. Okay. Let's see what we get. So I'm going to multiply this one by x squared on x squared. So we're not changing its value. And then we're going to multiply this one by x plus h squared on x plus h squared. So we're multiplying this one by that. We're moving that denominator over here and that denominator over here. Okay, everyone see that? So we can see it with numbers. It gets a little bit more tricky when we have to do it with letters, doesn't it? Okay, so that's our first step. Now, let's have a look at what we've got. I've got the same denominator for both terms, which means I can collect them together. All right, so what we're going to do next, basically, I'm moving from here, 6 on 8, take 4 on 8, to here. That's the step I'm going to perform now. So, we have the limit as h approaches 0. We have 1 on h. On the left-hand side, we're going to have 3x squared. We have the minus, and then we're going to have 3 lots of x plus h squared. Okay? And because the denominator is the same, we're bringing them all over the top of one denominator. Okay. Now this is the part. Let me not get ahead of myself. Okay, so we've seen when we have a radical, we multiply by the conjugate. When we have a fraction, what we're going to do is cross multiply the denominators. And that's always going to allow us to bring them together over one denominator. All right, now, same process. Expand, collect like terms. So, now I said, whenever we have multiple expansions, my recommendation is doing them slowly, right? You go your hardest though. X squared plus 2xh plus h squared. And I'm going to mirror good behavior up here. And then we'll distribute the -3. Now, this is where I'm talking about leave the denominator alone. Okay, we don't want to expand it. If you expand the denominator, you end up with this really painful expansion and it way overcomplicates things. Don't expand the denominator. All right, so I've done the expansion over 2 steps. First I did the perfect square, then I've distributed the -3, and now we're ready to collect like terms. So we've got 3x squared and -3x squared, those will cancel. Everything else has a h. So I'm going to factorize the h in the next step. That cancels. Okay, now we'll apply the limit. Okay, when we apply the limit, that means we're subbing h is 0 in. So we're putting a 0 there. At the top, we're going to have -6x. And in the bottom, we're going to have x squared multiplied by, that's going to 0, x squared. Okay, so that term's going to 0, x squared and x squared. Now we're just going to simplify. Yep, you go.
No, it's not.
Yep.
You're good.
So when we simplify, in the bottom we're going to have x to the 4, and at the top we've got one lot of x. So I'll simplify it over 2 steps. Firstly, I'll expand the denominator, and then we'll simplify by cancelling one of the x's. Okay, we have x. One of the x's at the top can cancel with one of the x's at the bottom. This is our answer. This is the slope function. All right. So now you've got enough skills to move on to those textbook questions. So what I'd like us to do right now, so you can demonstrate that you've grasped what we've just gone through. So we're exercise 2A. Let's have a go at question 3A and 5A. Okay, let's do both of those now. We've got one with the function in the denominator, and then we've got a root 1. 3A, 5A. Okay, so opportunity to practice both of those skills. So how close were you, Will?
It's because I was trying to take the h out of the both.
Oh, out of the denominator as well.
Yeah, that's the only thing I was getting.
Now leave that denominator alone.
Yeah, but once the denominator was left, I got it.
What's that? Do you know Pink Floyd?
Yeah,
You know the brick in the wall song?
yeah.
Yeah, we could come up with a, hey, student.
Leave those denominators.
Yeah. That'll be a good meme, hey? Thank you.